All right, so let's start. So welcome everyone to the Schubert seminar. Before we start, I want to announce that next week and 2 weeks after that, on December 2nd and on December 16th, we're going to have short talks by graduate students and early career mathematicians. So we start next week with 3 talks given by Kevin Summers, Peter Spacek, and Rui Xiong. And then there's going to be 3 other talks on December 16th. So I hope everyone can come and see what the young people are doing these days. And before that, we're very happy to have Professor Brendan Hassett from ICERM telling us about the rationality of twisted moduli. So please take it away, Brendan.
Thanks so much. It's a great pleasure to be at the seminar. I am really honored that I got invited to do this since I am not a card-carrying member of the Schubert community, but there's a few things I've been doing recently that have contacts, so I thought I would share them. I am putting a copy, a PDF of my slides in the chat, so if you want to move forward or move backward or focus at a different part of the slide than I happen to be on, feel free to do that. The work that I'm going to talk about today is joined with Yuri Tschinkel, but I also wanted to mention Tschinkel and Zhang, who is one of as a graduate student working with Yuri, and so he's also an important contributor to this project. Okay, so let me start with moduli spaces. And so today I'm going to work over a field K, and I'm going to look at one of the simplest possible moduli spaces. So the moduli space of n distinct points on P1 up to projectivity. I'm going to consider this over general field K. And so one way to think about this is I just simply take n copies of the projective line, and I remove all the diagonals. And then I take projective equivalence. And so let me see if I can do the pointer. Strangely, my pointer seems to have died. Try again. So here I'm removing any situation where 2 of the distinct points where they coincide. Okay. So let me take some examples for low values. For n equals 3 points. So I'm going to use the fundamental lemma that if you have 3 points in P1, which are distinct from each other, there exists a unique projectivity, taking the first point to 0, 1, the second point to 1, 0, and the third point to 1, 1. And I'm going to call these points 0, infinity, and 1. And a corollary of this lemma is that M03 is equal to a point, because there's a unique way of renormalizing P1, P2, and P3 to the standard points. A similar argument gives that M04 is isomorphic to P1 minus these distinguished points, 0, infinity, and 1. And you basically just take the fourth point, and the fourth point is distinct from 0, infinity, and 1, and so you get this open subset of the projective line with the 3 points removed. When you take 5 points, you get 2 copies of P1 with those 3 distinguished points removed, but you also have to remove the diagonal because the fourth and the fifth points have to be distinct as well. And so the explicit construction gives you an open subset of P1 cross P1, where you remove 0, 1, infinity on the x-axis and 0, 1, infinity on the y-axis, and then you remove the diagonal, and then what's left is the moduli space. So in general, if you want to describe the moduli space in a low-tech way as possible, just using elementary projective geometry, there's a beautiful paper by Sean Keel that does this. And so he used this perspective to compute all of the Chow groups of M0n, but we really just want to use it to give an explicit compactification. And so here we designate 0, 1, and infinity to be the first 3 points, and then we take the remaining points and send them to arbitrary points of P1 minus those 3 points, with the condition that we remove all of the diagonals. So if any of the points coincide, we prohibit that from happening. And so one consequence of this perspective is that we get a very concrete compactification of M0n bar, because if we simply allow the n minus 3 points, if we allow them to collide, or if we allow them to go to 0, 1, and infinity, we just get n minus 3 copies of P1. And so this is a beautifully explicit compactification of the moduli space, and one that we can really visualize everything that happens in quite concrete terms. But it has one huge downside from our perspective, which is that the symmetry is broken. So if I do this, if I treat 0, 1, and infinity to be the first 3 points, then the resulting description no longer evidences the symmetry among the endpoints. And so breaking the symmetry is a price that we pay for getting an explicit compactification of moduli. So I want to talk a little bit about the role of symmetry here. And so if you take an element of the symmetric group, then we can let this act on the moduli space just by ordering the various points. And so we take P1 through Pn, and we let the symmetric group act on them by permuting the indices. And this gives you a perfectly well-defined algebraic action on the underlying moduli space. Now, as I mentioned before, this concrete compactification, P1 to the n minus 3, is not compatible with this action. One way to see this straight away is that only 0, 1, infinity are kept separate, but the other points, P4 through Pn, they may collide with each other, or they may collide with the distinguished points. And there's nothing in the compactification that stops that from happening. And so this is a downside of this approach. But it's not so hard to repair this if we simply distinguish any I, j, and k from the set of points 1 through n. We can take an embedding, say, phi I, j, k of m0n to p1 to the n minus 3, where I take the ith point to 0, the jth point to 1, and the kth point to infinity. And then we can simply close up m0n using all these different embeddings into just an unreasonably large number of P1s. And this gives us a SN symmetric compactification, which turns out to be M0n bar, the Deligne-Knudsen compactification of the moduli space. And so so this gives us a way of getting a compactification that retains the natural symmetries that arose by permuting the points when they're distinct. Okay. And so one nice thing about this compactification is that at least when n is not too small, the automorphisms of the compactification are in fact just the ones that you would expect that come from permuting the endpoints. So this is a result I learned from Bruno and Mela. There are some exceptional cases like, well, M04 bar is P1 and it has lots of symmetries that don't really reflect the modular interpretation. But in higher dimensions, you do get the explicit, the only automorphisms come from explicit permutations of the points. One concrete example where you can see the compactification explicitly. So going back to 5 points, we saw that if we let the fourth and the fifth point float, we get an open subset of P1 cross P1. And here, the modular compactification is obtained just by blowing up 3 points, 0, 0, 1, 1, and infinity, infinity in P1 cross P1. And so this is an explicit realization of M05 bar as a blow up of the product of the projective lines. Okay, so maybe I should probably pause at this point. Are there any questions or comments before I start getting twisted? Okay, I will continue. So twisting moduli spaces. And so in some sense, we want to step away from our assumption that we have an ordering on the points. And so the ordering for our purposes isn't always the best thing to do. And so what we want to consider is a situation where we might have a collection of points, but maybe it's given by the roots of some homogeneous form in degree n, where the roots over a non-closed field don't necessarily come with a specific choice of ordering. Probably the simplest example is just the roots of a cyclotomic polynomial over the rational numbers. When we pass to the algebraic closure, we can choose an ordering, but the points over the algebraic closure, they will come with a permutation by the Galois group, just reflecting the Galois action on the roots of the polynomial. And so this is the situation that often happens over non-closed fields, where you're trying to understand arbitrary reduced subschemes of P1 rather than ordered sets of points. And so there's two approaches that you can take in order to understand this problem. And the first option is you just take the quotient of M0n by the symmetric group. From the standpoint of a moduli space, I don't like this very much. The reason why I don't like it is that the structure, the stack structure, gets messy when the points start to collide. You have non-trivial stabilizers. From my perspective, this moduli space is too big because, like for n equals 4, you're getting configurations of 4 points over every possible quartic extension. And I find that confusing and complicated. And so I'm going to take a different approach where instead of looking at all the possible configurations, I'm going to specify the Galois action. And so I'm going to stipulate how the Galois action permutes the points around. So I'm going to take as a basic input a map rho from the absolute Galois group into the permutations of our endpoints. And so an example is the cyclotomic action on the roots that I discussed in the previous example. There are other situations where you still get a cyclotomic Galois action over the rational numbers. And so I want to stipulate that action once and for all. And so this rho is how I will stipulate that information. Yeah, so I just want to emphasize here, I am specifying this Galois action. And so if we do this, if we stipulate the rho, then we can look at M0n rho we're going to take this to be a moduli space of pairs consisting of Z sitting in C over K, where when we pass to the algebraic closure, ZK bar becomes n distinct points, and C becomes P1 over K bar. I'm not saying that C itself is equal to P1. So in fact, this might not be P1 over K. I'm not insisting that it be isomorphic to P1. I have to live with the fact that it might be some genus zero curve with no rational points. That's a possibility I have to entertain from this perspective. And here, the rho comes in because the Galois action is encoded by rho. And so here I'm just insisting that this Galois action is given by the rho that we set at the outset. Similarly, we can consider an analogous definition for the compactification, M0 n bar. And so I'm not going to do that quite as explicitly, but I'll tell you how to do the descent in a moment. And so the descent datum for this moduli space is quite easy to describe. So if I look at our prescribed input data, the rho from the Galois group to the symmetric group, the symmetric group, it acts on M0n just by permutation of the points. And so whenever you have this a Galois representation on the automorphism groups, you can use this as descent data for a twisted form of M0n over the non-closed field. And so that's what I'm going to do. I'm going to interpret these moduli spaces as twisted forms of M0n and M0n bar. And these twisted forms are really what I'd like to study throughout this talk. And so let me give you an example. So I was told by Anders that to make the first part of the talk sort of accessible for students. So I'm sorry if I see leading experts in the audience, but I hope you'll be patient with me. So suppose that we have a situation where we're fixing a Galois representation on 4 points, and we take a corresponding degree 4 extension, or a tau algebra as the case may be. And then I want to construct a 3-dimensional vector space over the ground field K by using the elements of our extension that have trace 0. And I'm going to use this to get an embedding of spec L into P2. And let me just make clear that this is an embedding. I mean, I'm thinking about this over K. And so geometrically, the way to think about this is that I'm taking the 4 points of L and I'm mapping them into the plane in such a way that they're linearly independent. And so the automorphisms of these 4 points as a subset of P2, those you actually can write down matrices geometrically that induce the automorphisms among those 4 points. And so I really want to think of P of E as a twisted form of P2 using the this datum rho that I specified above via the action of the symmetric group on the sort of the standard coordinate points that I specified here. And so the basic idea is that if you let Z be spec L, this the 4 points with Galois action, and then I put it in P2. What I like to do is I like to consider all the plane conic curves. So these are curves C that contain Z, our 4 points, and are contained in P2. And so the picture here is, so I have 4 points in the plane. I choose a conic through those 4 points. And then the moduli space at M0 4 bar rho is simply the collection of all those conics. So I take the 4 points with the Galois action, and then I look at all the conics that are defined over K and contain that length 4 cycle. And so I can interpret this as basically the projective space of all homogeneous quadratic forms in the ideal of Z. And so by a basic linear algebra computation, you can see that these form a P1. Most of them are non-singular, but you might have some that are singular. So I might have some degenerate examples where I have a conic that looks like this. This is also fine. And so these are the elements at the boundary of moduli. So let me tell you the guiding problem. So let's fix N, Nk, and rho are Galois data. And so the question I'd like to ask is M0 and rho rational over the field K? And what I mean by this is that does there exist a birational map from projective space to a moduli space defined over K, over the ground field? And so the discussion that I just gave in the previous slide proves that these moduli spaces for n equals 4 are always isomorphic to P1. And so the answer to this question is emphatically yes for 4 points. Note that the underlying curves that you get, the conic curves that you get parameterized by moduli, those curves themselves may not be P1s. You may have non-split conics. You could even have empty conics over the reals, passing through a configuration of 4 points consisting of 2 pairs of complex conjugate points. The empty conics are fine, but the moduli space of such conics is still isomorphic to P1. Another question of a similar ilk that you could ask is, are these moduli spaces stably rational? And by stably rational, I just mean that for some R, the moduli space cross projective space becomes rational over K. And so this is a standard notion of stabilization where something happens after taking a product of something nice and simple. And so here it becomes rational after taking a product with some rational variety. And so these are the things I'm really interested in as research problems. And so I was told by Anders to take a break at some point, but maybe I should take the break just to give people a chance for questions or comments, and then I'll start presenting more results systematically.
Yeah, that sounds great. So yeah, let's take a break of 5 minutes, maybe 4:59, and meanwhile, everyone is welcome to ask questions.